Hi, ladies and gentlemen. We are looking at page 5 of our notes, and we are looking at notes 12.2, which are in reflections over axes as well as vertical stretches and compressions. So we have two different topics that we're going to be talking about in this class, or in this video. So make sure you're really focused on what we're talking about. So if you remember, when we did our mini transformations per unit, we looked at what happens when you reflect over certain axes. And if you remember, when we reflect over the x-axis, the y value turns to the opposite sign. The x stays the same, the y changes to the opposite sign, okay? And that's because it flipped over the x-axis, so it's changing its vertical position, okay? And then when you're reflecting over the y-axis, since you're flipping it over the y-axis, you're changing its horizontal position, so the y value stays the same, but the x value becomes the opposite. So question number 1 says to graph the following function below, then graph two reflections, one over the x-axis and one over the y-axis. Determine the equation of each function. So the first one, the first original function, is just a parent function, which is f of x equals x squared, but shifted 3 units to the right, okay? So hopefully by now you're good with parent functions that are quadratic. You know that the vertex is at 0, 0. You know you've got two symmetrical points at 1 and also at 4, right? Because 2 squared and negative 2 squared are 4, and negative 1 squared and positive 1 squared give you 1. So this is f of x. This is the parent function of f of x. So then, in order to graph this one out, we need to move it 3 units to the right, and then that'll be our new graph. So take each point and move it 3 units to the right. So 1, 2, 3, I did the right half of my graph, now I'm going to do the left half of my graph. So 1, 2, 3, and then here I've got 1, 2, 3. Okay, and then you connect those dots together, and this is really what f of x is. So f of x equals x minus 3 quantity squared. I'm going to delete or erase my parent function because all I want to reflect is f of x. So if I were to take f of x and I were to reflect it over the x-axis, then what would end up happening, this would stay right here, right? And then this would move down to the x-axis, and then you'd count it over 1. This is stuff you guys already know. So take this point, move it down to the x-axis, and then down one more point. To go from here to the x-axis, I would move down 4, and then I would move down another 4. And then same thing with this. To move from here to the x-axis, you would go down 4, and then move down another 4. So this right here is going to be your reflection over the x-axis. All right, so this we'll call g of x, but we don't know the equation of it quite yet. Then I'm going to reflect this original red one over the y-axis. So right here, if this coordinate is at 1, 4, I would count to the y-axis 1 spot, and then one more spot brings me to my reflection. Same thing with this one, 2 spots, and then take 2 more steps. Here you need to take 3 steps, 1, 2, 3, take 3 more steps to your reflection. You guys know how to do reflections over the y-axis, so I'm doing this quickly. This is 4 away, so 1, 2, 3, 4, take another 4 steps, 1, 2, 3, 4. And then this last one is 5 away, so take 5 steps, 1, 2, 3, 4, 5, 5 more, 1, 2, 3, 4, 5. This right here is my reflection over the y-axis. So we're going to call this one h of x. Now, what is the equation? Remember, we learned right here that if you reflect in the x-axis, the y value changes, and if you reflect in the y-axis, the x value changes. So you guys know how we write these coordinates out with function notation. We don't say x comma y. What we really say is x comma f of x. Okay, so let's write this out as x comma f of x. So then this means that instead of x comma negative y right here, this ends up being x comma negative f of x, because remember your y is the same thing as f of x. So the f of x becomes negative because the y becomes negative. And then same thing with this one right here. This would become negative x, and then f of x stays the same. So if I want to figure out what the equation is after reflection over the x-axis, I know that the original equation is f of x equals x minus 3 squared, right? So if I want to figure out what happens after I reflect over the x-axis, well, we just figured out right here that that this f of x value will become negative. So what I really end up having right here is negative f of x equals x minus 3 quantity squared. That's what happens when I reflect it over the x-axis. However, I'm not allowed to have a negative f of x right here. So to get rid of it, I divide both sides by -1, right? So then this turns into, my new graph right here will turn into g of x equals negative x minus 3, the whole quantity squared. All right, so g of x is equal to negative x minus 3, the whole quantity squared. This is for a reflection over the x-axis. All right. I want to verify on my graphing calculator that this really worked. So I'm going to graph out the original function, which is f of x equals x minus 3 quantity squared. Press enter. So there's my original function, and then my new function is g of x equals negative the quantity x minus 3 squared. So let's type this in, negative the quantity x minus 3, and then I'm going to square it. When you graph it out, it does appear to be a reflection over the x-axis. Now remember, if you press Control T, you can see your table of values, and if you look right here, all your values are the opposite sign for your y value, for your f of x value, okay? So that should make sense to you that g of x equals negative x minus 3 quantity squared, okay? So now if you were to reflect it over the y-axis, we learned that the x value becomes negative, but the f of x value stays the same. So if the original function is f of x equals x minus 3 quantity squared, that means that the new function, your h of x, is going to equal, now the only thing that's going to change is this x right here is going to become negative. So this is negative x, and then I copy the rest of it exactly the same. So negative x minus 3, the quantity of negative x minus 3, all of it squared. So let's go ahead and write this out right here. H of x equals negative x minus 3 quantity squared, right there. Let's graph it out and see what happens. So I'm going to Control T it to get rid of the table again. I'm going to press the tab button, and I'm going to type in negative x minus 3 quantity squared. There we go. That's a reflection over the y-axis. All right. So now let's figure out what happens, how we can summarize this information. So remember, if f of x is what you have before the reflection, and you reflect it in the x-axis, here your y values change. So that means f of x becomes negative f of x. Okay? When you reflect in the x-axis, the x values change. So this f of x right here becomes f of negative x. All right? All right, so let's talk about what your dilations will do to your graph now. So questions 2 through 5 say to graph the following functions using their parent functions and your knowledge of vertical stretches and compressions. So based on what we discussed in class, you should realize that you will have vertical stretches and compressions when the value of, when the parent function, the f of x, is being multiplied by a specific number. So let's talk about this. In question number 2, our parent function is f of x equals x squared. And again, you guys should know how to graph out the parent function for f of x equals x squared. So I'm just going to really quickly graph out my parent function. I would like you to do the same. Also, I strongly suggest that you color code this stuff so it's a little bit easier for you to understand how to do this, okay? So here, if you notice what's happening right here to go from this function to this function is that my f of x value, all of this whole entire thing is being doubled. So this means that y is doubled. Okay, so if you take a look at what you have for your y values right here, let's make a chart for your f of x values. Okay, so your f of x values, we've got -2 all the way up to +2. We figured out that our f of x values are 4, 1, 0, 1, and 4. So now if I want to figure out what my g of x values are, all I have to do is double all of my y values. So this is going to become 8. This is going to become 2, this is going to become 0, 2, and 8. So you are dilating the y values, okay? So this right here, you are making the y values twice as big. And the reason why I know it's the y values again is because x squared, which represents what y is equal to, y equals x squared. So this x squared is what y is, it's getting doubled. So when I double it, there's not enough room for the 8, so let's just put it approximately where it belongs. It'll be right here. And then at -1, 2, that's my new coordinate right here. My new coordinate after that is still 0, 0, because when you double 0, it stays the same. 1, when you double it, will become 2. And then 2, when you double it, will become 8. So this is what our graph will look like. Now, you probably said, when we were going over this, so this right here is g of x equals 2x squared, that the graph became skinnier. Yes, that's absolutely true. But what we really should say is that it is a vertical stretch. You're literally taking your graph and you're stretching it out. You're stretching it up. So it's a vertical stretch of scale factor 2. Okay, so let's take a look at what happens when we've got h of x right here. So again, our parent function is still f of x equals x squared. So I'm going to create my table of values again. So right here, I've got x, I've got f of x, and I know that my x values, we're going to go from -2 to +2, and then my y values will be 4, 1, 0, 1, 4. So then this here says that h of x is 1/2 of x squared. So again, you're taking the x squared, which is again the y value, and you're cutting it in half this time. So this here will become, this 4 will become a 2, this 2 will become a 1/2, this 0 will become a 0 still, all right, it'll stay 0, the 1 will become a 1/2, and the 4 will become a 2. All right, so then let's graph out the original function, the parent function, excuse me, so that you can see the relationship between the two. And again, if you color code it this time, it might be helpful. I'm not deleting or erasing the parent function, so that way you can kind of see it a little bit better. When x is -2, h of x is +2. When x is -1, h of x is 1/2. When x is 0, h of x is also 0, and then 1 will go with 1/2, and 2 will go with 2. Okay, so this is what my parabola will look like here. Okay, and this right here is h of x. And then don't forget to label this one right here f of x. All right, so remember when we talked about this last unit, we would say that the graph would become wider, but we don't really want to say wider anymore now that we know the proper vocabulary. What we'll really say is that it's not a stretch, it's actually compressed, so it's pushed down. So it's a vertical compression of scale factor 1/2. Okay, so let's go ahead and fill in this information right here. If you have a vertical stretch, it means that that f of x, when you've got f of x, it's going to be multiplied by a certain k value, but that k value has to be bigger than 1 in order for it to stretch out, to get longer, to get bigger, okay? And then if it's a compression, it's k times f of x, but the k value is between 1 and 0, okay? So what I'm going to do is I'm going to zoom in on this a little bit better, and I'm going to write it a little bit more legibly so you can write this properly. So this one right here is k times f of x, where k is between 0 and 1. All right, we'll bring this back to 200% so you can kind of see it a little bit better. The horizontal dilation we're going to talk about in the next video. All right, so let's take a look at questions 4 and 5 right here. So in number 4, we need to figure out what our parent function is, and our parent function is going to be 2 to the x power. So I'm going to make a chart with my x and my f of x values, and I know that my x values are going to go from -2 to +2 because that's just what I choose to do. And 2 to the -2nd power, right here, if I want to figure this out, f of -2 should give you 2 to the -2nd power, which is 1/4. Hopefully at this point in time I don't have to explain that as much to you. 2 to the -1st power is 1/2. 2 to the 0th power is 1. 2 to the 1st power is 2. And 2 to the 2nd power is 4. So when I graph these out, I've got -2 1/4. I've got -1 1/2, I've got 0 1, I've got 1 2, and then I've got 2 4. So when I graph them out, this is what my graph will look like right here. This is still my parent function. Now, the new function, it's saying that if f of x equals 2 to the x power, remember, 2 to the x power represents what f of x is. If this is -2 to the x power, you're going to multiply each one of your x values. You're going to multiply each one of your f of x values by -1. So this will become -1/4, this will become -1/2, this becomes -1, -2, and -4. So when you graph them out, here's where your new points are going to be. Sorry, this should be right here, right here, right here, right? I'm just graphing out what my table of values is telling me to do. So this is where my new graph is going to be. So this right here is g of x equals -2 to the x power. Now, if you guys notice in the last page, when we did this material right here, let me zoom out a little bit. We said that if it's a reflection in the x-axis, it's going to look like -f of x. So if our original function right here is f of x equals 2 to the x power, then -2 to the x power is -f of x, which means it's going to reflect in the x-axis, which should make sense to you. So we're going to call this a reflection over the x-axis. Okay? All right, and then question number 5, our last one. We're going to use our same table of values that we had before because our parent function is exactly the same. We're going to say our parent function is 2 to the x power. All right, so when I make my table, this one's a lot trickier. So please make sure that you are paying really close attention to how it is that we are doing this right here. So when I make my table, I've got x right here, and I've got -2, 0, 1, 2, and then f of x, we already figured out those values in the previous example, are 1/4, 1/2, 1, 2, and 4. Now, this time what's changing is your x value. The x value is changing, not the entire f of x value. So when I create my new chart right here, I have to be really careful. My f of x values are staying exactly the same. Okay, I'm going to erase this so I have some room to write some stuff out. My f of x values are staying exactly the same. It's my x values that are changing. All right, so instead of x being -2, it's going to become +2. Instead of x being -1, this becomes +1. Instead of x becoming 0, it stays 0 because the opposite of 0 is just 0. Instead of 1, this is -1, and then this becomes -2. However, your y values are going to stay exactly the same. So this is still 1/4, this is still 1/2, this is still 1, this is still 2, and this is still 4. Okay? So now what I need to do is I need to graph out the parent function and the original function so I can see the relationship between the two. So I know my parent function looks exactly like what we have in question number 4. So I'll go ahead and graph that out pretty quickly. So here's where my parent function is going to be. Connect your dots. This is what it looks like right here. And now when I do my my transformed function, this time instead of -2 is 1/4, it's +2 is 1/4. Okay? Instead of -1 is 1/2, it's +1 is 1/2. So if you notice right here, this is flipping over the y-axis. This is flipping over the y-axis. This is staying in the same spot. This flips over to the y-axis over here because it says -1, 2. And then the last coordinate is -2, 4, which is also a flip over the y-axis. So this is what this graph right here will look like right here. Okay? So this is, sorry, we forgot to put h of x there. H of x equals 2 to the -x power. Now, this should make sense to you. Well, first of all, let's write down that this is a reflection over the the y-axis. All right? And again, this should make sense to you because if you have h of x equals 2 to the -x power, what that means right here is basically h of x equals 1/2 to the x power. So if you look at this right here, our growth ratio is getting smaller. Let's connect our dots. Our growth ratio is getting smaller, so this is now going to be exponential decay instead of exponential growth. Okay? If you have any questions, let me know. I know there's a lot of information in this video. Mark down all your questions so that way you know exactly what you're doing. Have a wonderful day.